video lecture, we are going to move forward through Riemann-Stieltjes integral, and we are going to prove proposition 1.3. In the earlier lecture, we had seen how we can define bounded variation and total variation. Uh, we say that a function gamma from the closed interval AB to the complex plane is of bounded variation if it satisfies the equation, the inequality sitting here, and the total variation of gamma is the supremum of all such sums when we vary the partitions of closed level AB. And definitely V of gamma will be less than or equal to M, and that is strictly less than infinity. And also gamma is a bounded variation if and only if real part of gamma and imaginary part of gamma are of bounded variation. That is also a very simple idea which you can prove as the first exercise, exercise 1 will be this. It's a very simple workout. And also if gamma is real valued and non-decreasing, then gamma is a bounded variation, and V of gamma is equal to V of B minus gamma of B minus gamma of A. That is also left as workout for you. Both are very simple to do. And the next one is also, these are all just logical steps, so you can work out these this two preposition 1.2. Let's make the statement clear. So if you're given a gamma, which is bounded variation, and if you're given two partitions P and Q such that one partition is lying inside the other partition, then the sum which we discussed earlier with respect to the partition P will be less than or equal to the sum with respect to the partition Q. It is also very direct proof, direct logic. It comes directly from the definition sitting here. Exercise 1, 2 and 3. All the three of them are directly coming from this definition. And the second part you have to prove is if sigma is from closed interval AB to C is of a bounded variation, and if alpha and beta are complex numbers, then alpha gamma plus beta gamma is of bounded variation. That means if you have two functions of bounded variations, their linear combination is also bounded variation, and the corresponding V of alpha gamma plus beta sigma will be less than or equal to the term sitting here. That is also very direct proof. So let's move on to the preposition 1.3, which says that if you have a piecewise smooth function gamma from closed interval AB to C, then that gamma is a bounded variation, and we can find the total variation of gamma to the integral coming from A to B modulus of gamma dash of t dt. So first let's take that sum which we discussed while we were doing the definition, this sum. Okay. V of gamma p is equal to summation k is equal to 1 to m modulus of gamma of tk minus gamma of tk minus 1. So we are taking that definition here. And for taking that definition, already we have assumed that gamma is smooth. Okay. And we are we know that since gamma is smooth, gamma dash will be definitely continuous, and we are taking an arbitrary partition P which partitions the closed interval a b into subintervals which are closed interval t naught t1 t1 t2 t2 t3 etc tm minus 1 tm and t naught and tm are a and b respectively. Okay, and then we are considering that sum. Okay, and from this sum the term sitting inside the modulus, which is gamma of tk minus gamma of t minus 1, since this gamma is a smooth function, by the fundamental theorem of calculus we can say that whenever tk minus 1 less than or equal to t less than or equal to tk, gamma of tk minus gamma of tk minus 1 is equal to integral from tk minus 1 to tk modulus of gamma dash of t dt. So we are substituting that observation here inside this modulus. So gamma of tk minus 1, tk minus gamma of tk minus 1 is equal to integral from tk minus 1 to tk gamma dash of t dt. Okay, and by the property of the modulus and integral, when they are interchanged we'll get a less than or equal to summation k is equal to 1 to m integral from tk minus 1 to tk modulus of gamma dash of t dt. And what is this? Okay, so we know that this is actually the integral, the fundamental theorem of calculus can be applied on a particular subinterval, because since gamma is completely smooth, we know that every subinterval, if even if we are taking the domain of a subinterval, the corresponding image will also be smooth. So again we can apply the fundamental theorem here, and we get from this part you can get that that is tk minus gamma of tk minus gamma of tk minus 1, and then we have to apply summation k is equal to 1 to m, and so what we get is this. See, uh, for each of those sums, sum of integrals, you are getting gamma of t1 minus gamma of t naught plus gamma of t2 minus gamma of t1 plus etc plus gamma of tm minus gamma of tm minus 1. You have to just apply the fundamental theorem of calculus here. Okay, since the function is completely smooth, every part of it is also smooth, piecewise smooth. So you can apply that. And when you just cut the like terms out, the plus and minus, and you are getting gamma of tm minus gamma of t naught, which is sitting here. Okay, and that is nothing but, by fundamental theorem we know that that is nothing but integral from t naught to tm. T naught is a and tm is b. So integral from a to b modulus of gamma dash of t dt. Very simple. So what we got is that that sum which we needed for saying that it is a bounded variation, that sum is less than or equal to the sum sitting here, right? So that is of course a bounded quantity, integral from a to b modulus of a function. So we can say that gamma is of bounded variation. And of course, the total variation is a supremum of this value. So definitely capital V of gamma is less than or equal to integral from a to b modulus of gamma dash of t dt. So yes, and we already said that gamma is a bounded variation. So we prove the first part. Now we have to say that V of gamma is equal to this value, right? So we know that gamma dash is continuous, and also gamma dash is coming from closed interval AB, which is a compact set. So continuous image on a compact set, it will make us imply that it is a uniformly continuous function. So gamma dash is uniformly continuous. That means whenever epsilon is greater than 0, we can find delta 1 strictly greater than 0, such that whenever modulus of delta 1 Whenever modulus of s minus t is strictly less than delta 1, that will imply modulus of gamma dash of s minus gamma dash of t is strictly less than epsilon. Okay. And also we have the possibility of choosing a delta 2 greater than 0 such that we can form a partition P which is equal to T naught strictly less than T1 strictly less than T2 etc strictly less than Tm, and the norm of P is nothing but the maximum length of the subintervals. When we are considering the length of the subintervals, we have to choose the maximum of them, maximum of the length of each subinterval. That is norm of P. And we have to make the partition such that that maximum length of among the subintervals is strictly less than delta 2. We can have such a possibility. Then, and we are making the partition like that such that you know that integral from a to b modulus of gamma dash of t dt is nothing but the area of the region under the function gamma, right? So consider this part. This part is nothing but if you are having a function like this, see this is the function. We know that the area under the curve is the whole of the area under this part, right? So instead of that, we are going to make them into smaller rectangles. Okay. So what we are saying here is that we can make the partition in such a way that when we are finding the area of when we are finding the rectangle when we are forming rectangles and finding the areas of the rectangles under this curve and adding them up, the difference of the original area under the function gamma and this value will be strictly less than epsilon. We can find such a partition. Okay, so that is also a possibility since we know that gamma is smooth. So So in that manner, we can find a partition such that its norm is strictly less than delta 2. Hope you understood what norm is. Norm is nothing but when we are partitioning this closed interval AB, we are forming subintervals like this, right? T naught, T1, T2, T1, T2, etc. Tm minus 1, Tm, right? So what you have to do is find their length. Okay, if this is L1, this is L2, their length. That means T1, this is T1 minus T0, this will be T2 minus T1, this will be Tm minus Tm minus 1, call it Lm, okay? And you have to find the maximum among them, okay? The maximum among them will be called the norm of P. Simple as that. Okay, so you will be able to find such a delta 2, such a partition with respect to this delta 2 such that this is completely coming inside epsilon. Okay, so why did we choose epsilon here? Because we had an epsilon earlier and we have to link them both when we are going further. Okay. So here just consider this tk to be some point lying on closed level tk minus 1 and tk. Okay, fine. Hence, just removing the modulus signs, we know that if something is modulus of f is strictly less than epsilon will mean minus epsilon strictly less than f strictly less than epsilon. So take the right hand side of that and then bring this term sitting here into the right. That's how we obtained the inequality here. Okay. And this term sitting here can be replaced with the term sitting here because why? Because gamma dash of tk is a constant. Okay, so you can work it out there. Okay, and then what you have done is this is less than or equal to, you have epsilon and this term here, here also epsilon and this term here. Okay, and you're just adding one more term inside. Okay, this term, right? Now if what now we are going to do is we are forming a partition again, which, as mentioned earlier, is strictly less than delta. I'm taking it to be strictly less than delta, and this delta is the minimum of delta 1 and delta 2. So we can form such a partition at our own likeness. Okay, so then if this is so, we know that modulus of gamma dash of tk minus gamma dash of t is strictly less than epsilon by the first uniformly continuous property. We assume, we said that if s modulus of s minus t is strictly less than delta 1, that will imply modulus of gamma dash of s minus gamma dash of t is strictly less than epsilon, right? So here whenever the maximum length of a subinterval is strictly less than delta, that will imply obviously that is strictly less than delta 1 since it is the minimum. Okay, so when we are taking the subinterval tk minus 1 tk closed subinterval, definitely that will be, the length will be strictly less than delta 1, and we are taking tk tau k from this interval, and t is coming from this interval. That means the modulus of tk minus t will be strictly less than delta 1, so that condition is satisfied. So we get this inequality. Okay, and now we are considering integral from a to b modulus of gamma dash of t dt, that is less than or equal. We know that this is equal to b minus a, right, from the fundamental theorem of calculus. So we are adding some more things to make it an inequality according to our need. Okay, this is less than or equal. We know that this is equal to b minus a. We are adding some more things. Less than or equal to epsilon. Epsilon is a positive quantity plus epsilon times b minus a. That is again a positive quantity. Obviously, that will be greater than or equal to b minus a. Plus, we are adding the sum which is associated with the bounded variation. Okay, fine, and this is equal to epsilon into 1 minus 1 plus b minus a, plus it is denoted by v of gamma p, right? And this is less than or equal to epsilon into 1 plus b minus a plus the total variation. Obviously total variation is the supremum of all such possible sums when we vary the partition p. So this will be definitely less than or equal to this term. Now what you have to do is you have to make our epsilon go to 0 plus, and that gives integral from a to b modulus of gamma dash of t dt to be less than or equal to v of gamma. So earlier we said that v of gamma, from the earlier section we got v of gamma is less than or equal to integral from a to b modulus of gamma dash of t dt. Now what we obtained is integral from a to b modulus of gamma dash of t dt is less than or equal to v of gamma. So that means that our theorem is proved. V of gamma is equal to integral from a to b modulus of gamma dash of t dt. Also we proved that gamma is a bounded variation. That's the preposition 1.3, and do work out the exercises we mentioned. I can show it to you once more. The first exercise is that if gamma is of bounded variation, show that real part of gamma and imaginary part of gamma are also bounded variations, and also gamma is, if gamma is real valued and non-decreasing, that means if it is a monotonic function, then gamma is a bounded variation and the total variation can be calculated like this. And then the preposition 1.2, note that as earlier said, all of these can be just found out by using the sum of the bounded variation, the sum which is associated with bounded variation and logical steps from that. Uh, so work on them, and thank you for joining. See you in the next lecture.